video lesson, we'll deal with the fourth objective on our stoichiometry chapter, practice test C. We are being asked to calculate the theoretical yield, actual yield, or percent yield given appropriate information. A little background where the theoretical yield is the answer to our stoichiometry problem. It would tell us that if we achieve 100% yield, that would be the expected maximum. The actual yield comes from experimental data. What did we get from actually running an experiment? We compare our actual to the theoretical and come up with what's called percent yield. Percent yield is a measure of the efficiency of the reaction. Reading through our first problem, it says, hydrobromic acid reacts with aluminum metal in a single replacement reaction. We would then begin by writing our balanced equation. Hydrobromic comes from hydro root word ic. We need to find bromide, and acids of course begin with H. Hydrobromic acid would be written as HBr. Reacts with is the plus sign, and aluminum metal is Al. HBr plus Al begins our equation. In a single displacement, aluminum would kick out the hydrogen from our compound HBr. Hydrogen, now written alone, is a diatomic molecule, H2. The product then, aluminum bromide, would hook by charge. We get Al with a +3 and Br who's a -1. AlBr3 is our other product. Looking at balancing our equation, I notice that H's and Br's are together on the left side, and I have 2 and 3 of them on the right side. We'll need to turn those both into 6's to balance the equation. And to do that, we start with a 6 HBr, 3 H2's, and 2 units of AlBr3, and then finally repairing the aluminum. A 6:2 to 3:2 stoichiometric ratio. We'll read through the letter B. If 1.2 times 10 to the 24th atoms of aluminum react with excess amounts of hydrobromic acid, 790 grams of aluminum bromide are produced. They are telling us in the story problem the actual yield of our product, aluminum bromide. And of course, since we didn't run the lab, we would need to be told our actual yield. We can calculate the theoretical yield and compare the two in a percent ratio. Beginning with 1.2 times 10 to the 24th atoms of aluminum as our given, we will work the 3 steps of stoichiometry: divide, ratio, multiply, and target the product, aluminum bromide. And I want to match those units to what was provided for the actual yield, grams of AlBr3. Given the number of atoms, we'll calculate a mass. To cancel the number of atoms in our first step, we would write 1 mole of aluminum is 6.02 times 10 to the 23rd atoms of aluminum. When we are counting, we use Avogadro to convert to the mole. In the heart of our problem, we compare what we want over what we're given. We want 2 moles of AlBr3 set over the given 2 moles of Al. A 2:2 stoichiometric ratio. And to land at our gram unit of product, we'll need a molar mass. I'll add up 27 for the aluminum, 80 times 3 for each of those bromines. Then I get 267 grams of AlBr3 in every 1 mole of AlBr3. Hitting on our calculator, I get 1.2 E24 divide by 6.02 E23 times 2/2 times 267, and I find 532.2 grams of aluminum bromide. This is known as our theoretical yield. To find our percent yield, how well did our experiment work? We take our actual, which was given to us as 790 grams. We set that over 532.2 grams, and we express that as a percent. Comparing these two numbers, it's obvious that our actual is heavier than our theoretical, and sometimes we've noticed that in the lab when our product is not completely dry. 790 divided by 532.2 times 100 gives me a percent yield of 148.4%. The actual yield was heavier than the theoretical yield, creating a larger than 100% yield.